Hi, my name is Harris Hosh.
I'm Pei-Sheng Ye.
My name is Soo-Young Jang. Today we'll be discussing our amplifier design. First, let's look at our circuit schematic. We have three main parts to our circuit. The first is the differential amplifier that you see here, and also we have a cascoded circuit here to increase our output resistance, which allows us to get a very high gain. Next, we also have this bootstrap circuit to create the biases we need for our cascoded MOSFETs, as well as the iReference. We also have some of the parameters that we use for our PFETs and MFETs here. To calculate some of the biases that we had to use for our cascodes, we use the following formulas, and we have implemented these voltages from our bootstrap using different dimensions of our transistors. Here's the list of our transistors and their sizes, and we can see here that our total size is about 0.09 millimeters squared. Next, we also did a DC sweep, or a transfer characteristic, to find out what our large signal gain is. From here, we have calculated the gain to be 214,000.
For the CMRR, we first performed a differential mode sweep comparison, which we used a frequency sweep with differential mode setup and observed a gain of 106 dB. Similarly, with another frequency sweep, with the inputs connected to a common source with a low gain of negative 84 dB, we were thus able to calculate a CMRR of the differential mode over the common mode to be well over the specification necessary. For the input swing, we set up the amplifier as a unity gain and performed a DC sweep over the input. This allowed our amplifier to have an input of 0 volts and still reach clipping level at 2.29 volts over the input swing range needed. Within the output swing, we performed a large signal sweep, and we see again the output swung at 1.86 volts, which is within the amplifying region. Again, for stability, we used the unity gain setup, and we found that we had a phase margin of negative 116 degrees. Thus unity gain to be at negative 116 degrees. Thus our phase margin was 64 degrees, which is greater than the 45 degree spec needed.
We come back to an AC sweep of our amplifier operating in differential mode. By looking at the negative 3 dB point, we see that our amplifier has a bandwidth of approximately 4.9 kilohertz. Next, we subjected our amplifier to a step input. By looking at how fast our output responds, we can get our slew rate of 124 volts per microsecond. Next, we use a noise performance tool in Multisim to get the output referred noise over bandwidth. Then we can approximate the input noise by taking the output referred noise over gain. And we get an input referred noise of 18.4 nanovolts over the square root of hertz. And then lastly, power dissipation. We looked at how much current our amplifier was drawing from the source, and then multiplied that by the source voltage to get 7.25 microwatts.
This concludes our demonstration. Thank you very much.